Thank you. Welcome everyone to the Timber Design Society webinar series, the first one of 2026. And we're starting with fully threaded wood screws and high load bearing capacity and compact connections. And today, Jörn Rüschenschmidt and Rodrigo Mendes are taking us through the presentation. We want to thank our sponsors up front that are supporting us throughout the year. Rotoblas, Mytech, iBuild, XLAM, TechLam, ProLam, Eurotec, and Simpson Strong Tie. All of those support us in many ways throughout the year, and we're really grateful for them to be our sponsors. Before we go to the webinar presentation, let's see what's coming up next. So in the next TDS webinar in March, on the 19th of March, we'll hear about fire and CLT, especially about the linear joints, presented by Sebastian James from Rotoblas. And upcoming TDS events are, as you probably have seen in our newsletter or on LinkedIn notes, is seminar. It's a TDS roadshow this year. Two seminars, one in Christchurch on the 21st of April and one in Auckland on the 23rd of April. So look out for the link to register and come and join us. And the other exciting bit this year is we've got the Timber Design Awards happening on the 26th of June this year. For that, the entries close Friday, the 6th of March. There's a link provided here if you want to take a snapshot. Otherwise, visit us on the Timber Unlimited website. And this seminar on the same day, which is Timber Delivered, real projects, real experience. So it'll be really interesting to join in. So if you are the day in Auckland, have a look. If you want to get tickets for this, it's happening before the gala dinner. With that said, if you have any ideas or any suggestion on technical notes, any topics that are up there and you've been discussing with your peers at work or outside of work, feel free to scan this QR code, join on Slido, and flick us a note on what you wanting to hear more about or what you want us to answer in the next webinars, or as well tech notes published in the journal. From the journal, we get into today's program. Let me introduce Jörn and Rodrigo now to you guys. So Jörn Rüschenschmidt is the Global Sales, Timber and Engineering Head of Global Technical Advisory Team. Jörn joined Eurotec in 2014 and had led complex and large-scale timber and decking projects worldwide, including over 100,000 square meters of elevated outdoor structures and numerous mass timber developments. He leads Eurotec's Global Technical Advisory Team and is driving connector and development and providing technical design support to clients globally. And then we have Rodrigo, who joined Eurotec in 2022 as a founding member of the Global Technical Advisory Team. And he's supporting clients with practical solutions on complex technical challenges across the international market. He plays a key role in Eurotec's screw design guide and CLT design guide development and manages ICC approvals while contributing to high performance connector innovation. And that said, I'll let the two guys jump on board, share the presentation, and present today's webinar to you.
Yeah, thank you, Bjorn. I'm sitting in beautiful Auckland, so not as last time where it was midnight in Germany where I was awake, so made it a bit easier to be in time and being on the road the whole week in New Zealand, hopefully seeing many faces, which are now also in the chat. So let's see what we can add on to what some of the people might have seen already here in New Zealand. So Rodrigo, would you mind starting the presentation? Because I just then can click on, makes it a bit easier.
Yeah.
There we go. Perfect.
There it is.
And so, yeah, I just want to go
Just
briefly in the type of production because fully threaded screw are slightly produced different than we showed last time on the complete range. Then Rodrigo will show the structural properties, and then we go a little bit into the challenges which even may make the best design fail, on-site handling and other points impacting the correct use and application of the screw. So, yeah, I just skipped now the introduction as Bjorn already made this. I think we have this still in the PowerPoint. Let me just see if I can continue. One. Oh, would you mind clicking on because it doesn't seem to react onto my clicking. Just says controller
Now,
video. Wait a second. Yeah, perfect. I skipped this. So I'm in Eurotec since 12 years. Rodrigo joined us now 4 years ago. We both are part of the team, which consists of more than us, but we two have the honor to be with you guys. And we talk about our Constructs fully threaded screw range. So looking at this, the production slightly differs from partially threaded screw. Any screw is done from the same steel alloy, and the differentiation starts in the final parts of production as well as also slightly in the hardening process. So we work from 17 MnB4 steel, which is inserted in the machine, always comes in cones of 1 ton, and then 8 different steps can follow depending on the length, the diameter, and the type of screw. So first of all the wire gets divided into length, which you see here. So the wire is fed in the machine. The video might be a bit stuttering, but it is all a so-called inline machine. That means all steps or the first steps happen on one machine. And then we differentiate. They might stay on one machine or they might be moving to two other parts of the machinery to get a fully threaded screw. So first the wire is loaded onto a motor, so it's driven actively in the machine. It gets straightened and stretched, and then we divide them into length. So the screw always is a shorter and thinner wire than the final screw. Seeing this die size of 445, this will be a 6 mm screw. So the core is 445, but it gets rolled out to the width of 6 mm, talking about the nominal diameter of the thread. So our wire is always matching the core diameter, which for example here is 445 for 6 and 575 for an 8 mm screw. They got cut into length, and as they are stretched, you see the little straight piece of wire on the bottom right. This is the first stage of any screw. The next step will be we forge the head. The head is forged often in 2 steps. We have one machine doing 3 steps. So that means we first have the wires. So the 3 dots you see on the top left is a top view on the screw. We first have the wire, then we bulge it out to a rough pre-forging geometry. And the second step then brings them into the final shape, including the drive as well as the imprint on the screw, which might be the type, the length, or even a brand logo. Then this is called the pre-forging, done by a special mattress, which grabs the screw from the side. The round cavity covers the top, and then a little pin shoots through the hole, makes the first geometry. The final forging, you see the die is a bit more detailed for the milling ribs and more details. So the die grabs the now pre-forged screw from the sides. The little piece comes on top, and then the pin with the Torx drive punches in and forges in the drive. Next step will be we normally then roll the thread. So all fully threaded screws mostly start as partially threaded screws. That means by rolling the thread, we stretch the screw, and you see the tip even gets black. So we never actually induce any heat in the process. The heat created is just done by the material moving. So it's always cold forging and cold rolling. Any heat occurring in the process is just due to the material getting hot by dissipating the energy of the forging process. The next step then is maybe a milling station. You might know this type 17 tips, which have the so-called cutting notch. So for this type, the screws are always fixed, and a little saw blade mills out the notch, which is known on many screws. The other tips, like the drill point tip, they get punched or pinched at a different machine. But by this, we always end with a partially threaded screw on the standard machine. Now we differentiate if we have a screw longer than 600, up to 600 or even up to 400. This now differentiates the forging process, meaning the next step is for the extremely long screws. Here the screws are first done on the machines you saw. Then they get moved to a separate machine where we roll the thread to get the full thread. That means the two rolls you see on the top right, they catch the first thread and then they roll on, producing the final thread, which should be now seen in the video. Yeah, it's a bit stuttery, but now the screw gets moved in between those two rolls and becomes a fully threaded screw. This is how we do big diameters, so 10 or bigger, so 10, 11.3, and 13 in our case, of 600 or even up to 1.4 meter, which is the longest screw we produce in the facilities in Hagen. If we have a screw up to 600, we either can produce them like that, which wouldn't be efficient by numbers. We mostly do this on a big roll forge you see on the bottom left. This roll forge, we just need to forge the head on the first machine and to forge the tip or pinch the tip, and then they get hung in a rack and rolled through this roll forge and get forged or rolled through the full 600 millimeter of thread in one single move. For small fully threaded screws up to 125 but high diameter, so 10 and 12, or in this case 10 and 11.3, they can be done on a multi-stage press. So only for a partially threaded screw completely run on one machine, we have to differentiate as soon as we come to fully threaded screws. Our newest addition is a big thread roll that can do 400 millimeter from raw wire up to the fully threaded screw, which can work up to 11.3 by 400. For this machine, we first also might need to pinch the tip. We can skip those two machines, so we might need to pinch the tip depending on the type of screw, but this screw in general can be produced all in one step. This arrived last year. It's a beast of a machine. It has a forging pressure of up to 80 tons. It does 90 screws per minute, and every hour we run up to 5 kilometers of wire through this. We can do up to 100 millimeter long, partially threaded, or 400 fully threaded. This is now shown in a little video. Again, excuse the stuttering, but this is just caused by the bandwidth maybe. So here you see it's the same procedure. We got the raw wire on a cone. The wire is stretched and straightened. Then the wire is cut into length. Then we start forging the head in two steps as we do for partially threaded. There you see the forging pressure. Then we roll the first thread. A robot turns the screw that now the point which faces to us now faces to the back of the machine. And then a second thread roll will roll the remaining 200 millimeters of thread on top of the machine. The videos are all on YouTube, so they can look at them without any stuttering. But we also send more details afterwards to our registered member. And there you see coming off the machine a fully threaded screw with a length of up to 400 millimeters, 13 millimeter of diameter, as well as the tip all forged on one machine. As this was the first part, now Rodrigo will continue with some more structural properties and details on our Construx fully threaded screws.
Okay, let's see here.
I need to click on, there we go.
Thank you very much, Jörn. Well, I will go a little bit more deeper on the details of constructs, applications, characteristics, and advantages, and the latest developments we had on it. So all construct screws, except for the 13 millimeter diameter one, the E12 constructs, have either ribbed countersunk head shape or cylinder head shape. The countersunk head shape can be used either on wood-to-wood or steel-to-wood connections, given that the holes on the steel plate have the correct shape to house the head of the screw, and the cylinder head shape are specially designed for wood-to-wood connections, where the screw is a very small volume and it can be used on very small spaces, and it's the only screw, the only head shape allowed on our ETA certificate to be installed further from the wood surface. So if you want to completely conceal the screw and with a plug or with a wood paste, then this is the head shape you need. And also, almost all the construct screws in the construct family have a drill tip. I'll go further on the details of this drill tip on the next slides. Just to hover over the whole constructs family for you to know, the construct cylinder head 1 is available on 5.2, 5.9, 6.5, 8, and 10 millimeters of thread diameter. And it's available up to 1 meter of length. And the countersunk head shape one, all the diameters I mentioned, but the 5.9 up to 1 meter of length. And these ones with carbon that are made of carbon steel and have a drill tip, they don't need pre-drilling whatsoever. Then we have constructs 11.3 that is available up to 1 meter of length also. And in this case, for the longer ones, we recommend pre-drilling for precise installation. And constructs stainless steel A4 ones available in 6.5, 8, and 10 millimeter of diameter. In this case, our ETA requires it to be installed with pre-drilling because of stainless steel being a softer material than harder carbon steel. And they are available up to 500 millimeters of length. They have a reduced torsional strength, and that's why pre-drilling is needed. And the biggest one, the Constructs E12, the 13 millimeter diameter one, can be used on either wood-to-wood and steel-to-wood connections. Their pre-drilling is usually needed because usually the longer ones are used for reinforcing, especially suited for heavy-duty reinforcement of big mass timber elements like glulam beams. And in this case, you really want the screw to be there on the exact place to reinforce the timber component on the stresses. And it has a superb characteristic torsional strength of 113 Newton meters that even allows it to be installed without pre-drilling. And you can see that video here of constructs 13 by 1 meter of length where Jörn installs it. And it is available up to 1.4 meters of length. This screw has been already used, for example, on a 1 meter deep glulam beam in Brazil, reinforcing against compression perpendicular to grain. And also was used on CLT to CLT connections on a project in Chile where there are very high seismic loads. So it's a screw that has been already proven in many projects. And about the applications, sorry, the constructs fully threaded screws are, well, as you know, all the perpendicular to grain stresses on timber components are a weakness on timber. So in this case, fully threaded screws are an ally to reinforce the timber on the zones where there are high peak of perpendicular to grain stresses, as this pitch cambered beam here, where fully threaded screws are reinforcing the pitch region, where there's a very high concentration of radial stress here that tries to open a crack approximately in the middle. And the fully threaded screws, you can see that it sews the potential crack, preventing it from opening. And here, like I mentioned, on a compression perpendicular to grain support on glulam beams and on notch glulam beams here, where there's a high concentration of tension perpendicular to grain that tends to try to open a crack here. Fully threaded screws are very useful in this matter. And apart from reinforcement, of course, main secondary beam joints, where the fully threaded screws are used as shear tension screws. These are so-called shear tension screws because they are used on a shear plane, but these screws are used inclined. So in this case, they are considered to be exclusively loaded actually. Going to the drill tip feature of the constructs, this special drill tip has the main advantages of this drill tip is that they prevent wood cracks during installation because they greatly reduce the force by when installing the screw on wood. This it subjects to less stress on the wood when it is installing, and it also reduces the torque needed for installation. This increases the durability of tools needed for installing the screw, and also reduces the fatigue on installators. And of course, also allows, this is one of the main advantages, that it allows a reduced minimum spacing requirements, and this is backed by the ETA certificate. As you can see here, a graph here of the insertion moment of the screw, what is being installed. You see here on the x-axis the screw in depth, and the y-axis the insertion moment. You see here how the torque needed increases the longer the screw is. And in the case that the tip is not a drill tip, this is much higher. So this makes that the torsional strength of the screw has to be much higher to endure this insertion moment needed for installation. One of the requirements for the screw to be approved in the ETA is that the characteristic torsional strength of it has to be 50% higher than the mean insertion moment of its installation. And in this sense, the drill tip has a great advantage and gives more reliability on the screw while installing, preventing the screw to break while installing it. Regarding the minimum distances for axial loads, as I mentioned, the fully threaded screws are mainly used for in axial loads, where the screw is loaded axially, either in compression or tension. Here you can see many applications, for example, the beam-to-beam joints with cross screws. Also here in reinforcing in compression perpendicular to grain. Here on beam doubling. And here are the minimum distance requirements. So you can see here the rules that are related to the diameter of the screw. And here all the main diameters of constructs. And here's the difference that the drill tip makes. The standard on ETAs for example, the A1 and A2, A1C and A2C requirements that they are here. You can see they are the minimum distance to the edge and wood end grain. The standard for the ETA, if you don't have any data, is that for A1C is 10D, and for A2C is 4D. As you can see, the drill tip allows it to be half the requirement, the standard requirement. So 5D and 3D, and for all the diameters of constructs. Some manufacturers have a slight advantage of, for example, 7D here, but only for the smaller diameters. And this is where the difference makes for having a drill tip, that many times in the timber design, there are very small space to house all the screws, and there's a very good advantage in having these reduced spacing requirements. One of the recently the newest members of the construct family are the 5.2 and 5.9 millimeters of diameter, and one of the main applications are main to secondary beam joints, as you can see here. This is one of the charts that you can see on the product data sheet of the screws. And these small diameter screws came from the demand on projects that used very reduced timber components with very small timber sizes. So you can see that you can use, you can join, for example, a main beam and secondary beam with a width as small as 60 millimeters of width. And this wasn't possible, of course, with the former 6.5 that we had. So this kind of tables are very useful for quick design and pre-design also. And the latest development that Constructs had is that we made a whole new test on the characteristic withdrawal parameter of it, where we tested much more samples. As you know, wood is a natural material with natural defects. So naturally, the tests done have a great variability. We increased the number of specimens, of samples, and this reduced variability allowed for the characteristic withdrawal parameter to get closer to the maximum value of the whole test data. So in this sense, for the 6.5, the increase in the characteristic withdrawal parameter was 36%. On the 8 was 13%, and on the 10 was 6%. And this has already been greatly priced for the design. This is a comment that we have been receiving. And it's also valid for the A4 versions because the characteristic withdrawal parameter is not material dependent. It is just geometrical dependent. So also for Construct A4, these new values are valid. And also for the ABS strong screw, that is a plate screw, that the only difference is that the head shape is specially made for steel plates. Also, I like to mention that the constructs can be used with Taurus 45-degree washers. These washers are used with steel plates, and they have the advantage of being able to use thinner steel plates. And on a large bearing area, you create more stiffness this way. And there's 3 different sizes for the 3 different diameters of constructs Contourson head one. And this is the great advantage. If you don't have these 45-degree washers, as I mentioned, you need to the steel plates to have the correct shape to house the shape of the head of the screw, for it to have a correct bearing and to correctly transmit the forces without creating an unwanted failure mode. And it, of course, steel is expensive, and if you need a very thick steel plate to do this milling, and also the milling process is expensive. So with using this kind of washers, you just thicken the plate where you need it, where the screw is. Like you see here, it is correctly correct housed, and the forces transmit correctly without having to waste material when it's not needed. And we have in the product data sheet, you can see the design tables for each diameter and compare between different diameters and the same timber thickness. You can compare the resistances between the 6.5, the 8, and the 10 millimeter of diameter. And last but not least, there's the cyclic bending test that we did on the University of Canterbury, New Zealand. We know that in earthquake-prone zones, the timber structures need to be designed with so-called capacity design, which means that the connections have to be ductile enough to dissipate the energy of cyclic loads. So they can go on the plastic on plastic behavior, the joints, while maintaining an elastic behavior on the timber components. And for this, it is needed to ensure that the fasteners, for example, have enough ductility. One way to benchmark this is by using the cyclic bending test according to EN 14592. And this test is done then to determine the low cycle ductility class of the screws. The test comprises first three different screws that are subjected to the monotonic test to evaluate the yield or maximum moment capacity. And then 3 other screws are subjected to a cyclic test with 3 fully reversed bending cycles and a final monotonic ramp. As you can see here is a 3-point bending test. And these are the screws that were tested. The constructs stainless steel 6.5, 8, and 10, and constructs of carbon steel 11.3 and 13 millimeter of diameter. And in the past, we have done also for the carbon steel construct 6.5 and 10. I just mentioned them here. Here you can see a sketch from the test setup according to the standard. And here a test photo from University of Canterbury. So the screw is bended always on the threaded portion. This is a mandatory on the test specifications. And it is measured the bending moment and also the bending angle. This is the bending angle, just for you to know, because I think it is. I don't know if it is shown. Well, it must be shown on the standard, but you can see here a sketch I made. And this is basically the graph that you get from the test. Here you can see the monotonic test, 3 curves that are monotonic. You can see they are a little bit stiffer than the cyclic tests. And here the cyclic tests, 3 also. You can see 3 fully reversed cycles, and then the final monotonic ramp, as you can see here. It's important for you to know that the test comprises 3 classifications, the S1, S2, and S3, being the S3 the most stringent one. So if a fastener gets a S3 classification, it means that it is ideally ductile, so it got the highest classification of ductility. And for it to pass this class, 3 criteria must be met. So in the criterion 1, the screws tested monotonically shall reach a certain max angle without breaking. On the criterion 2, the screws tested cyclically shall reach this same alpha max angle without breaking during the final monotonic ramp. So even if they do the cyclic part, okay, but on the final monotonic ramp they break before reaching this angle, they don't pass the test. And finally, the criterion 3, the screws tested cyclically shall achieve a mean residual bending moment at least 80% of the mean moment capacity. That means, like here on the final monotonic ramp, this difference here on the maximum bending moment that you get here on the cyclic test, it has to be a maximum 20% of difference between the maximum that is reached here on a monotonic test. So it's really strange, very strict criterions. And you can see here on the summary of results that all of screws tested passed the S3 ductility class. And for you, for the ones that want to have a little bit more details, we can send the test report. Okay. And also here you can see The previous ones that were tested, construct 6.5 and 10 millimeter of diameter, harder kaolin steel. Then I'll give back to Jörn.
Yeah, thank you, Rodrigo. So two little additions to Rodrigo's parts. So the 13 millimeter has also been used on projects here in New Zealand already. So it has been used even locally. And there will be more testing coming with Canterbury as we are currently setting up a little work group to see that we test even not only practical applications, but even tailored applications, how they are done here in New Zealand. Coming up to the thing in the design, often the design and the reality differ because in the end, the best design can be failing if we have the wrong installation. So I think it's quite important to know how the change of angle is affecting the screw and how we make sure that your design, especially working with inclined screws, will be maintained on site. So if you look on the left graph, so seeing laterally loaded screws, we have a perfect efficiency if we are at 90° on the lower part, so perfectly perpendicular to grain. And if we are complete with the grain, we lose a lot of the capacity. You see, getting down at an 8x270, for example, from 6 kilonewton to just 3.2. But especially when we look at the angled installation of screws, where we always aim for the 45 degrees, I guess many people are not aware how a change in angle will change the effectiveness of the screw if we differ from the intended axial load direction. So being at 44 or 43 will not be of a big change. But as you see, as soon as we come to 40 degrees, for example, we reduce by approximately 7%. And the more we go into the shear plane, we reduce even up to only 30% of the initial capacity of the screw. So this is caused by two things. First of all, we try to load the screws always perfect into the screw direction, meaning we utilize the tensile capacities and the thread embedment in the fiber. But as soon as we get off this angle, not only do we get more into a shear plane, we also get much more into reduced embedment as the screw gets shallower and less screw is inserted into the anchoring substrate. This is really important to consider that the angle needs to not to be exactly on point, but there is reduction to be assumed, meeting not the right insertion angle. But to hold on this, it's quite important to the workers on site know how to maintain this. And by this, when I was still working on site, we built ourselves jigs, just cut some MDF, cut some ply, get a 45-degree ramp just to have the screws at an angle. So we tried to get this pain also away from the workers by just making a simple jig, which is simply a plastic part, which is a simple, which is a simple angle template. So we just made a simple plastic part, which is 45 degree on one side and 65 on the other side. And also there, the drill point tip comes into point. If you ever try to set and screw straight at an angle, even with a jig, it will start dancing around because just the spiral curl of the thread will move the screw along the top surface and not really push it forward, except you already apply excessive pressure. With a drill point tip, which is more a milling process than a drilling process, to be honest. You mill a little pocket, you can set the screw at 90 degrees without being already in the grain, and then you can lay it in the ramp and install it by moving forward. So it's really important to at least instruct the workers to use somehow a 45-degree jig to get your screws at an angle, because otherwise you lose your capacities even with the perfect right design. So in this case, design, quality control, and installers have to go hand in hand. I know a big topic here is hydrogen embrittlement. And this was a topic for us when we made the step from a distributor to becoming a producer in 2013. This was the first and only time we had proven HE embrittlement on 3 screws. So people always look at the hardness as a benchmark, and you can roughly say, yes, the lower the hardness, the lower the risk is for hydrogen embrittlement. But if you control your process, even hardness above the 360 or 390 HV can be completely free of production induced embrittlement. So when we look at this, we have the hardening process, which up, one push too much. Let me see if it go back. Where can you make click back? I think I'm gonna click for, there we go, perfect. So the hardening process in this case works in different stages. So we have first of all the increased heat, then we have the carburizing phase, which you see, unfortunately, sorry, but the drawing I only had in German from our production installations guidelines. So aufkohlen means carburizing. That means we induce carbon gas into the material. Then it's slightly cooled down, kept at a certain temperature. Then we increase the heat again, which hardens the core as well as the outer perimeter of the screw. Then it gets cooled down. Often we use, for example, oil for quenching. We don't use water, so it's still a fast cooling down, but not as fast that it gets brittle or even crystal hard. And then again, the screws get tempered one more time. That means we really make sure that we have a smooth and homogeneous molecular grid in the screw. The next thing, so after this, we do a HE testing, which I will show you 2 slides later. So we have 2 stages where we test for HE. First of all, after hardening. Secondly, after surface treatment, because you also can induce HE unwantedly during the surface treating phase. So the next step then would be to go for the surface treatment. In this case, we do galvanics. First of all, the hardened screw gets degreased, pickled, and one more degreased to be clean, that you really can put the surface treatment onto the surface. They are called into so-called drums with satellites that prevent the screws from tangling up, because screws can really tangle up. We call it, they become a hedgehog because they look like this. And by this, we really make sure the screws get an even treatment and don't tangle up and don't become like a big lump of screws. And the next step then is the different types of electroplating. If you use a standard sink, you have to keep your sink substrate kind of diffusion open, that even hydrogen can diffuse out of the screw. The more layers you put, like special treatments, like clear coat treatments, the more you might catch up the hydrogen in the screw. So just the standard sink coating is the one that least due to HE, but still there what we do after the process with having the sink coating on there, which is diffusion open, as I explained, we still temper it one more time to be sure that the molecular grid is relaxed and that all the unwanted materials diffuse out of the screw. After both steps you saw, the hardening as well as the surface treatment, we still do our HE testing. So for the HE testing, we install the screw either to a spacer tube, into a steel plate, or directly on a thicker steel plate. So what we do, this is done once per each production batch after heat treatment and surface coating. This test is to be done within 24 hours after those steps. So the block is clamped into a vise. We install the screw either as option 1 or option 2. Then 5 screws are tightened by hand to the 90% characteristic torque we define in the ETA. The screws are left in there for 72 hours, and then we check the screws. If the screws crack during this 72 hours, there is embrittlement happening in the screw. That means the whole lot will be blocked. If the screws stay tight and there is no relief, no cracking screws, then the screws are approved. The screws even have to sustain the uninstallation. And as you know, when you install a screw, especially on a steel to timber connection, you have to maintain a reduced torque, and to break them loose, it takes an increased torque, even often 25% more than for the installation. That means if they last the uninstallation and still have the ductility, they are not embrittled. Also, part of our QC is that the screws have to fulfill a minimum bending angle. So even having a hardness over 390, we maintain the ductility by checking the bending angle, which is not part of the ETA certification. It's internal QC that we have different bending angles the screw need to sustain based on its diameter and fully threaded or partially threaded layout. So we really check all the screws frequently, exceeding the hardness of 390, that they are free of embrittlement when they leave production. However, there are factors on site that might be the issue, like heat, saline water, wet timber. Over-torquing is quite a thing. Even a correctly hardened and produced screw free of HE will have a brittle failure when you over-torque it. For this reason, we have 2 little aids. First of all, just a screw insertion tool, which easier allows you to control the screw. So it locks onto the screw and you can handle a longer and high diameter screw easier on site, especially on angled installation, working overhead or without the loss of losing it. You see the sleeve? The sleeve on the bottom is drawn back, so the screw is locked into the sleeve. As soon as the sleeve, like it is on the top picture on the bottom left, is touching the timber as it's spring loaded, it snaps back, releases the screw, and allows it to be set properly. As Rodrigo said, countersunk heads always flush with the surface. And more important is the second part, which can be used separately, which is the torque limiter. So the big little round thing you see on the right. The torque limiter is just used in two options. We have an 18 Newton meter and a 32 Newton meter version. If you look at anything that is steel to timber in particular, a shear connection, a tension strap, and even lifting and rigging, you need to be sure that the screw is fixed to the right torque. You might not even see the screw head tearing off, but over torquing it will cause that the screw just might break, even at a shallower point, not directly at the head, but somewhere in the drilling channel. So in the worst case, there is nearly no embedment and the connection has no capacity. So this is quite the important things to look at, that even if your design is done flawlessly, there have been peer reviews, there have been the LODs, but in the end, knowing what issues can happen on site with a correct produced, correct designed screw without the worker knowing how to handle wood screws might cause failure, in the end, even catastrophic failure. And any breaking screw, whatever is producing it, or any failing timber structure will harm not the producer of the screw, not the installer, but the whole industry. So it's quite important to have an eye on the complete chain from production to design to installation, knowing how screws are to be designed and to be treated on site. Yeah, that's it from our side. Again, we will thank you for your time, and being in New Zealand is really amazing, getting feedback and so much acknowledgement and support from the industry being here the whole week. So thanks for having us. And now, Bjorn, to you looking at questions.
We can't hear you, Bjorn.
How about now?
There we go.
There you go. It's too many buttons to push yet. So yeah, thanks, Jörn and Rodrigo, for running us through this, showing us the production and how you get around the hydrogen embrittlement in the manufacturing. We've got a few questions. We've got a few minutes left, so let's go through those. First questions we had from one of our members was, what's the reason for not having a hex head screw? Can countersunk screw head be used on non-countersunk steel plate holds?
Not. So for this application of the non-countersunk steel plate, we got this ABS screw, which is a dedicated angle bracket screw, which has the flat bottom below the cylindrical area. So the hex head screw, just as we are a European producer, is rarely used in Europe, to be honest. If you look at our EDA, which you can find on the website, you see we have the hex head option for the construct screws, but the majority is just countersunk, which is flush with the timber surface, the ABS screw, so angle bracket screw, which is meant especially for non-countersunk holes, and the cylindrical to be drawn under the fiber according to ETA.
Thanks for that. One question that I think is quite important for all of us engineers, when the screw is inserted into the timber, how would you inspect it if it's installed properly or not? And how can you see it from the outside? What's your suggestion on that, Jörn?
This is the biggest problem. So if the screw is installed properly or improperly, you rarely see it. Sometimes what you can do is simply just take a little hand wrench with a torque bit and move it, and especially on small diameter screws, so 5 and 6, if they are over torqued or have snapped, you can move them because they always break quite close to the head. On long screws, however, this is the risk, what I said, if you don't use them with the correct torque, you don't see the breakage because the weak spot of a partially threaded screw is always the transition from thread to shank. So you can pull them out as they have no thread behind the brake. But the fully threaded screws snap somewhere, rarely on the head. If you over torque them, it's first the stretching, then the thread deforms, and then they snap. So that means the only way to maintain this is controlled installation torque using jigs and torque limiters in the end. So for QC, it should be like mandatory that people prove the jigs they have at least also show that they roughly have the right angle, and that at least there's 1, 2, or better 3 torque limiters on each side, matching the diameters that are used in that project.
So rather than taking screws out, you suggest to set up a proper QA protocol for people to prescribe that in their specifications, probably for us as well, to make the contractor aware of it.
Should be part of
The
health and
next,
safety.
yeah, good point. Does the load capacity reduce when using softer woods with higher moisture content? So that's probably a very, very interesting question for us here. What's your thoughts on that?
Rodrigo, you want to go?
Can you repeat? Is if the reduced spacings depend on the density?
Now, how does the capacity reduce when we use a softer wood with higher moisture content?
Well, in that case, with the higher moisture content, when in that case, for fully threaded screws that are mostly used, as I mentioned, in axially loaded, there's a factor that I think it's the K mod factor, that it depends on the service class that the joint you're designing. So that according to European standards, the EN, the Eurocode, this factor goes, I think, from 0.6 to 1. So the more moisture you have, higher moisture content you have on the screw, on the timber, the less resistance you'll get. For example, this is made with this factor.
Yeah, looking at this, so the Eurocode is class 1, 2, 3. So 3 would be external, which often requires stainless steel, which reduces the capacity of the screw just by the K mod value, which is part of the design guide that we have on the website. So if you look at the Eurocode 5, for all the screws, we mentioned the safety factors to be considered. And also all the values we have are mostly based on 380 kg per cubic. So we already seemed quite a soft wood for most of the capacities, but for sure it had even to be reduced in case of service class 3, so exceeding the moisture content of 20%.
So thanks for that. I'll just here quickly, because then we can answer another question. In New Zealand, we do have a factor that you can apply to your design capacity if you go beyond 15% moisture content, which would be basically for you service class 2, 15 to 20%. And as you said, beyond that, service class 3 to fiber saturation, it's only for external structures, hopefully. We don't hope that you're reaching those parameters in internal structures anyway. So it's part of the planning process. Coming to the next important one is, and I think that's one thing from New Zealand, is what's the compliant pathway in New Zealand for these screws? You mentioned the ETAs in Australia, but what's the suggested approach that you have seen being applied in New Zealand so far?
So interestingly, the most in New Zealand still a lot of carbon screws, as well as, let's say, like rusted or zinc nickel plated screws are used in certain applications, even in treated timber. So in the end, our approach is looking at highly treated timber, having even some, not looking even at the old one like the copper chrome arsenate, even looking at modern treatments, which are less harmful but still aggressive. For this, normally, if we look at the T classes, which we have in the Eurocode, they would define any treated timber having acidity or treated components in there to be used at least with a stainless steel, which could not be. We also have some hardened stainless steel, which is easy for 1.0 for certain screws. But in the end, the sheer application as we see it as a European company, as soon as we have a treatment which is acidic or anything else, a coated screw will not or should not work at all, especially with increasing moisture. This should be done with stainless steel. And what we also did for testing, we installed several coated screws like Rüschenschmidt, Maxshow, zinc nickel, how they are all named, into timber. We uninstalled them and then cut the timber piece in half. And what you see that none of these additional coatings and even the sink itself is not really abrasion proof. That means on long screws, often the first 30% of the insertion channel wear off your coating. So when we talk about excessive coating, even submerged partially in water or H3, 4, even 5, it should be a stainless steel screw. However, we had many projects here with excellent panels who were also treated in a service class 2 environment where sink was no issue at all. So for sure, this again depends on increased moisture and how the treatment even then gets washed to the screw.
Right, I think that was partially answering the question before this one about how you use specific fasteners in and harsh environments with H3.2 treated timber. So I think that was good covering that. In terms of compliance path, ETAs, well, obviously are an alternative solution. However, most projects that we apply these anyway. However, screws are covered in 1720 to a part. So are you saying that people using ETA approvals using the New Zealand timber design standard and have seen that is usually no problem at all, or how would you just explain it to an engineer if they would ask you?
So in the past, the ETA proved as the most common standard, and even looking now at CLT2 box where we are inserted, so they all have the EDA capacities, and they cover this for the AS and NZ parts by using our ETA. So at the moment, the ETA is sufficient. Closing the loop to the testing, so looking at the local standards. So this is why we made this work group, to have even more knowledge about how this transitions into the local standard compliance. Rodrigo, anything from your side? Because I think all the projects so far we handled here and supported, we used just the EDA.
Yeah, that's right. I think it's all requests we had from Australia or New Zealand. They always asked for our ETA information, and it seems like they're allowed to use it. I think it's maybe similar to Chile. In Chile, they can either use the Eurocode or even our ICC certification, which is specially made for United States. Yeah, so in that case, I think there's no problem to use the Eurocode approach on New Zealand.
Well, it's more and more common to use these screws, and it's becoming common best practice to use ETA approvals because they have a more stringent QA than other screws, common screws produced in the country or also elsewhere. Because in New Zealand we don't necessarily have regulations on the production, whereas in Europe they do. So therefore, there's more rigorous control around these screws. So the compliance path is still an alternative solution. However, it's easier to bring through because it's becoming a common practice. So that's what we're seeing here. There are ways.
ETA requires a third-party audit, whether you're going to produce in-house or even out-house according. You have to mention all your facilities in your ETA with the code HW, and by this you have to comply to third-party audits, auditing your in-house production as well as even the outsourced production. So the QC on the screws, even if not produced in Europe by a third party, are still the same that would apply to an in-house production.
Mm-hmm. Well, I think we do maybe have time for one more question. The last question here was answered already previously with your comments slightly. So cross screws and beams to beam connections, how do you validate the torsional restraint to beam ends? The screws cross over at the secondary beam neutral axis to LTB restraint resistance is from lateral bending of the screw. I think what is asked here is how do you check and validate the torsional restraint against lateral torsional buckling, and how do the screws interact with that? I don't know if that's something we can answer quickly here, or do you guys want to do this off the screen in more detail afterwards and get back to the person?
Yeah, that's an interesting question. I think we'll be happy to answer with an email later. Yeah.
Okay. All right. Thanks for joining, everyone. Thanks to Jörn, you and Rodrigo for presenting and answering questions. Thanks for Engineering New Zealand to facilitating this, and I'll see you all in March for the next webinar.
Thanks
See you,
very
everyone.
much. And see you in June on the Design Awards.
And see you in June on the Design Awards.